So maybe let's start. We invite Tobias give his third lecture on this mini course. So can I see the first without the set of where is the title there?
It's okay. It's I think the students know it's I forgot my own title.
Okay, please, yeah.
How you cannot see the forest without the trees or something like that. Okay, so you see the, do you see the notes? Yes, you do, no?
Yeah.
Okay, so yeah, welcome back everybody. And so before the break, I was just telling you that if you have that we want to consider particular polynomials in particular which give rise to a collection of conditions. And what we were considering d tuples, and we were looking at polynomials on the natural numbers, which are non-negative on the non-natural numbers, which have exactly d zeros. And I just painted you some pictures to give you some idea how they're looking like. And then the main theory for necessary condition is saying that if M is realizable, then this is true for all Fp. And here I made a mistake. It's true. I can have here a K, and K has to be less or equal to D. So I have to have it for polynomial of first degree, for polynomial of second degrees, for polynomial of third degrees, and up to the maximal degree. So for example, in the case d equal to 2, so what we get, so if we have k equal to 1, then the only polynomial which we have in k equal to 1 is f is equal to x. And so we get the condition that L of M underline of x is greater or equal to 0, which is one of the one we know. It's just that M1 is greater or equal to 0. In the case k equal to 2, the polynomials looks like we had before. It's like x minus alpha, x minus alpha minus 1, and alpha is a natural number. And so the conditions which we have, so L of f greater or equal to 0 is the same, and you can easily compute that, as saying that M2 minus 2 alpha plus 1 M1 plus alpha times alpha plus 1 is greater or equal to 0. And the Yamada condition was a special one among them, somehow the best. And now we can easily ask, okay, now we found a set of necessary conditions. Are this condition actually sufficient? And the answer is no. I will create you another condition. Okay, so assume I have M1 is equal to 0. Then what does it mean? It means that 0 has to be equal to the sum j equals 0 to infinity j p of j. But j is non-negative, p is non-negative, so it means that j p of j is equal to 0. And so that means for all j's unequal to 0, so that means for all j element of n, so I have here, notice here I have no 0 here, I have then that p of j is equal to 0. So this implies that p has to be the probability which is concentrate at 0. And so in particular, this implies that M2 has to be equal to 0. So we get an extra condition, and the condition is M1 equal to 0 implies M2 equal to 0. And now, no, this is particularly bad. So first of all, why it's not included in the upper conditions, you see they're always of the form that M2 is greater or equal to something. Yeah, so you can never get something like M2 equal to 0. How you should get that? It's not inside of this condition. So this is an extra condition. Okay. This is worrying because we found something, we have no idea where it's coming from. I just randomly found it. And it's interesting, another interesting aspect of this condition is that you would I mean, just thinking about linear algebra, you have to fulfill one condition, which is that you get M1 right. So you would think that you will lose one dimension. Yeah. And here, actually, you lose more dimensions. You actually force everything else. So there's some kind of collapse. And you see, but this collapse comes from the fact that things are non-negative. I mean, this trick here wouldn't work if the p's were not assumed to be non-negative. Yeah, that's where all the trouble comes from. In some sense, we boxed ourselves into a corner, and out of, because I mean, the non-negative is somehow it's given by a corner, we're boxed in the corner, and then there's no way to escape. And so that should be a warning sign that this is not like linear algebra. It's not like solving linear equations. Okay. So again, we are somehow forced to step again a step back, and this leads us to what he's doing. Okay, sorry, I have to restart that 1 minute. For some odd reason, I don't know how to get rid when this is happening. So
Reshare, stop, and then share again. Yeah.
Share button. Oops.
Good.
Okay, here I'm back. So I want to take a step back, and now I come to section 3. And this is a so-called Chakalov Bayer. I mean, the Chakalov theorem is from the 40s, and then it was only completed in the 90s. So you see that it's not such a trivial theorem. So what this theorem is telling us? Oops. So the theorem is telling us the following thing. So if M1 up to MD, so this tuple, which are called underline M, is realizable by a probability P, then there exists, I can find D numbers in the natural numbers and, sorry, D plus 1 numbers and D plus 1 non-negative numbers, such that also, sorry, yeah, and I have another condition here, they sum to 1, such that also if I do the if I construct the following probability, the probability here should be D plus, oops, D plus 1 and L as well, Pj delta J also realize. So I forgot to open the chat.
There is a question.
Yes, I found that. If Emma. Yes, exactly. That's exactly what it means. I mean, that is exactly what it forces. Because if the mean is 0 and all the probabilities are only on positive integers, the only way how I can get it is that I put all the probability on 0. So I have 0 with probability 1 and all the rest I don't have. And so you see that there goes some forcing on, which has to do because you want a non-negative solution. If you would allow P, the probabilities to be negative, you could find a lot of other solutions. So, and so what this means here is that I have sorry, this is wrong. So maybe I shouldn't call this J. Let me call it I. We call it I, so I have here Pi, and then I have here Li. So I have this probability J, which is given by that. So what it means that the probability of J is equal to Pi if J is equal to Li, and it's 0 otherwise. Yeah, so it means there's a probability which is 0 except at these places which are given by L1 till LD plus 1. And that's exactly why I tried to before. You remember when I was doing it in the case 2, I tried to get away with 2 deltas. I mean, with 2 probabilities, which is kind of elementary probabilities. And in the case D equal to 2, I tried to get away with 3 of them, because I can always do that. Yeah. So it was not such a crazy idea of me doing that, because I knew obviously this theorem, and so you can always do that. On the other hand, you see that the complexity of this problem will very quickly go out of hand, because you will have a lot, as I told you before, if you have the linear, somehow the conditions you have will only fix the p's, but it will not fix you the l's. And so you will have a lot of choices which you have somehow to control what is actually going on there. Okay, I wanted to prove the Chakalov theorem, but I don't think that I have the time to do that. And so I don't want to rush through that. And I want to come to the part which is more important to finish my storyline. So the Chakalov Bayer-Teigmann theorem actually works also in general if you have not only a probability on n, but you have a probability on an arbitrary subset of an finite dimensional space RD, then if you can solve the moment problem, if you can fulfill this kind of D conditions, you can only do this by D+1 Dirac measures. And so it's a good news, because it means that it should be computable. If you have enough computer power, you can do it. You just have to check this one case. You don't have to check infinitely many cases. So this is already a very good news. And the difficulty lies here in the thing that you have n0, so you can have could go in principle arbitrary large. Okay, so now I skipped the proof of that, and you can find all the details for our case in the lecture, because you can give actually very elementary proof. In this case, the general case is less elementary. So, but now I will go to section 4, and I will explain what are the necessary and how I get to get necessary and sufficient condition. Okay, so by Bayer-Teigmann, so by Chakalov-Bayer-Teigmann theorem, which I just wrote above, I can always get away with D+1 points. And I will not use this information, but note what that means. Note that this means, because it means that P has only finitely many points at which you have to a probability. So it means that there exists an N such that P of J will be 0 for all J greater or equal to N, sorry, greater to N. Okay, so this will motivate me to what I call 4.1, and this is, I will do now the truncated moment problem. So the same problem, but instead of n0 to infinity, I will do it on n. I will explain you what is nn. So what is nn? I mean, this is somehow has no meaning because I didn't tell you what it is. So nn is, I just define it as a set of 0, 1 up to n. Yeah? So I just look at a finite piece of it. And to do that, I need to use a theory which is called convex analysis. And I cannot assume that all of you know that. And so I will repeat what it means. So convex analysis is very similar to linear algebra. So I give you first some definitions. So if let V be a vector space, I think about R2, R3, something like that. And C is a subset of V. Then we say C is convex whenever the following holds. Whenever. If you do the following things, you take 2 points V and W in V, and you take 2 numbers, alpha, beta, real numbers, such that alpha and beta are non-negative and alpha plus beta are equal to 1. Then I have alpha, sorry, I made a mistake here. There should be in C, so then our set C, then alpha V plus beta W is also in C. Note somehow the similarity with what one has in a definition of a linear subspace. No, a linear subspace of a vector space is exactly the same definition, only that one doesn't have these 2 extra conditions. And you note also that this is exactly the situation which happens when we use this probabilities. We always had this kind of parameters which had to be non-negative and they have to sum up to 1. And then we have the analog of a linear combination. It's a convex combination. So a convex combination is, as you could imagine, is something like alpha I vi, I equal from 1 to n, where vi are in our vector space, the alpha i's are non-negative, and the alpha i's sum to 1. And then you have the analog of a convex hull, of a linear. So of this somehow the analog of linear combination. And now you can look at the minimal linear space spanned by a set of vectors. So let S be a subset of V. Then the minimal convex space spanned by S is defined as everything which I can write as a convex combination. Okay, I need to write my set S as I number the things, and I is a general index set. And so what I have is I have to take all sums I, alpha I, vi, such that alpha I is greater or equal to 0, and the sum of alpha I is equal to 1. And now I have the problem of, I don't want to have the problem of convergence, or I actually want only to consider, better to say, only finite combinations. So I make a nexa condition, only finite many alpha I are actually strictly greater than 0. Now you only allows in the theory of linear combinations, you only allow finitely many combinations of that. And then we have the following general theorem. This is in the lecture notes. This is theorem 4.1. So let S be a subset of ID finite, which has only finite many elements. And S is not contained in a d-1 dimensional hyperplane. Then I can do the following thing. I have a representation. So for the convex combination, from the convex hull of S, so the smallest convex set which contains all of S, I can write this as an intersection over half planes, half spaces. So where H, so the script H is a collection of all closed half spaces that contain S and D and the bounding hyperplane so the bounding hyperplane contains D points which do not belong to a D-2 dimensional affine subspace. Okay, this is a lot to take in. And this representation is, and it is minimal. So, and it's minimal in the sense one cannot exclude any H in A without destroying the equality. Okay, let me give an example to make that clearer. So think about D is equal to 3. So in D equal to 3, to characterize a hyperplane, which would be a plane, an affine subspace of dimension 2, which would mean a plane which not necessarily goes to 0. So in 3 dimension, to fix a plane, how many points I need? I need 3 points to fix a plane. And this is somehow exactly why I said that the bounding plane of the half space. So the half space would be the plane and everything on one side of it. So it means that the bounding, so it would mean that to fix a hyperplane, I need 3 points. And these 3 points should not lie on a line. If they lie on a line, they would not fix the hyperplane, would not fix the plane. So that is exactly the second condition, that they don't span a D-2 dimensional affine subspace. So the D points must be somehow spread enough so that they span a D-dimensional plane and so fix this plane at all. And so what it means, so for example, a classical, if I have some points, then the convex sets are given, it's given, oops, there should be a straight line. It's given by something like that. And then what would be an example of one of these hyperplanes? So here in 2 dimensions, so I should have 2 points on it for my S. So I could take this plane here, and then this half space would contain my convex body. And you see that using 4 other of this kind of half planes, I could perfectly identify this convex set. And this is exactly the one which have to go through 2 of these corners, where these 2 corners are not lying on a line. I mean, this is later is also clear if I have somehow here a straight line, and let's say I have 1 point of my space S here, 1 point of my space S here, 1 point of my space S here. So I have this convex. So the convex set of it is this here. Here the convex set was actually the square. So if I have this convex set here, then if I have another point of S on this line, no, then sorry, in 1 dimension, no, that's a stupid thing, forget it. So in 1 dimension, I cannot do that. I need at least 2 dimensions to have this kind of effect. In 2 dimension, I could just add another point on the boundary, which is not good enough to span things. Okay, so why this kind of theorem is of any use to us. Okay, to which kind of set S I want to apply it? The set S I want to apply it to is the set of all S, which looks like that. L square up to LD, and L is in N0. Okay, so what is then the convex hull of S? That are all the vectors which are of the form sum k equals 0 to D, sorry, 1 to D, L to the K, alpha K, such that alpha K is non-negative, and the sum of the alpha K is equal to 1. Now, a hyperplane, what is a hyperplane? So in this context, a hyperplane how this hyperplane H looks like, it will be something which will be of the form, will be all vectors in RD such that A0 plus A1 x1 plus AD xd is, let's say, greater or equal to 0. I mean, you could make easily smaller equal to 0, but this is a convention. I mean, like in two dimension, a plane is given by some coefficients ax plus by plus c is greater or equal to 0. And now, so what means that conv S is a subset of H? That is nothing else than to say that for all so to say that S is contained in the hyperplane, what does it mean? It means that I have to check that this pointer inside. It means that for all L element and 0, I have that A0 plus A1L plus A2L squared plus AD LD is greater or equal to 0. And here now you see how we come back to our polynomials. And having D points, and the second condition, having D points in S means that there exists L1 to LD in N0 all different such that we have equality. We have equality here. We have equality in. So that is, if we can reinterpret this in terms of polynomials. So if we introduce f of x equal a0 plus a1x plus ad xd, then what I wrote here just means the following, that it means the following. It means that for all L in N0, f of L is greater or equal to 0, and f has d zeros on N0, on Nn, sorry. Okay, and so we see that we have to classify these polynomials. How does these polynomials look like? Okay, we have a first family, which I call PDN. So these are all f's, which are in our previous set PD, such that the highest coefficients which I have in my description will be inside of our range. No, so the last zero will be still in our range. But I have another family of polynomials which before didn't appear, which I now call curly Q dn, and these are all polynomials. These are all polynomials where additionally the highest term is of the form minus xd. How I can have something like that? So this was not, before this was not possible because we extend to infinity. So if I have my line, I have here n and I have here 0, then I can have now a following kind of polynomial, which, for example, is 0 in 0. It goes like that. Goes 0 at an integer, it comes back at an integer, the next, sorry, and then it goes like this. So where the integers, we have here 1, 2, 3, and so on. No, this is not negative. So these are polynomials which have the following in general. They have the following form. They have the form Rn times f alpha, with alpha is in alpha d minus 1, and Rn of x is equal to n minus x. And you can just think a bit about it, that this is essentially the only possibilities you have. And so our polynomials which we're interested in is the class P dn union Q dn. And so we are ready to write our main theorem. So this is theorem 4.2. So if n is greater or equal to d, and I have given moments, putative moments, m1 to md, then then this is realizable by a probability P if and only if the functional LM of P is greater or equal to 0 for all P from this two sets of 0, and the condition is minimal, and this is the conditions are minimal. So let me recall that if, sorry, this is, should I call polynomials F, not P? Sorry. Because the probabilities, I have the problem that I have probabilities P and then the polynomials, which one also likes to call P. It's not possible, so let's call them F. Okay, so if I have a polynomial F of X, I recall you what this functional was. So if I have A1 of X plus, we had this before, then Lm of F is just A0 plus A1 M1 plus AD MD. So this theorem gives us, is realized by a probability, and I should say that here, I forgot that on the natural numbers up to n, if I have this kind of condition and you see somehow n appears here and n appears here again. So, but I found a set of necessary and sufficient conditions, and they're also minimal. So you may be misled, and this is a common misbelief, that necessary and sufficient means that it's minimal, but this is not the case. So assume I have some necessary and sufficient condition, I found some of them, and I have further necessary conditions floating around. I can just add them to my set of conditions, and it will stay necessary and sufficient, because adding more condition will keep it sufficient, and it was and because this condition was necessary, it will also keep them necessary. So I can always, if I have further necessary conditions, I can add extra rubbish. So I can always produce more and more condition. Obviously, that's not what you want. You want to have to as few as possible condition to be checked, and so you want to have it minimal. And so minimal means if I remove one of the conditions, the theorem will fail. And we have also this one, so you can really not get rid of any of these conditions in general. You have to do something more complicated to get rid of them. So let me try to prove that theorem. So proof. So I mean, recall that if I look at the case moment of the measure where the probability is concentrated as at L is L to the K. So it means an element in convex is always of the form is always of the form L. I have to sum over all L element n. I take alpha L, and then I take my vector. So I take here L squared to the LD, where alpha L are negative, and the sum over L element n of alpha L is 1. I mean, n, this set has only finitely many elements, so we don't have to worry about this finiteness condition. We just put things 0 to get that. Okay, now, but these are the moments of the following probability. I write the probability P, which I write as a sum L element n n alpha L delta L. Or in another way of saying it, P of j is equal to alpha j for all j element n. And then I have that the moment if I look at the vectors of moment, so I look at the vectors of moment m1 up to md of p, this is exactly the same as what I have here on the top. So I see that these moments, so if I interpret this as a vectors of moments, that conv S is nothing else than the sets of all moments which can be realized by a probability P. Because we go one way around. If I start with an element in conv X, so I'm given my alpha L, I define this probability like here, but I can go obviously also the other way around. If the probabilities P are given here, I can define this vector like that. And so I see that conv S, so the convex cohal of S is the set of all M under which are realizable on N. And then the theorem follows by our general theorem about convex sets, which I gave you the general theory of convex sets, because this condition on the hyperplanes, we already retranslated this forms in terms of polynomials, and it's just exactly what I write here is nothing else than the statement of this classical theorem. And so, but this result has a defect. It depends on the n. We wanted to have a solution on n0 and not for a fixed n. So what we can do to get rid of this n. So in the final section, I will do the truncated moment problem. On n0. Okay, so we know from the Shakalov, sorry, total misspelling here. By a Teichmann theorem that if realizable on on n0, then we have realizable on n. But if you have realizable on an n, then you have also realizable on n prime for any m prime greater or equal to n. How you can see that? So if p n realizes on an n, then you can define Pn prime. You just define it as for j, you define it as Pn of j if j is less or equal to n, and the rest you put 0. Yeah, so you can always extend this. That's somehow you can do this. Aha. So maybe we can try to use that to get rid of our condition, of our n dependence. So we had somehow first, we had that for all f element p dn, we had Lm of f is greater or equal to 0. But this is subset our previous set of PDs of all polynomials where the zeros came in pairing integers, because this is just the extra condition that the 0 has to lie below n, but this n we could always make it larger if we want, so it would be maybe reasonable just to drop this assumption and we get a condition here which doesn't depend on n. On the other hand, we have for all f element qdn, we have also Lm of f is greater or equal to 0. Okay, but how these polynomials look like? This polynomial f are of the form Rn times an f alpha, where the f alpha is an element of the polynomials of pair, but the one with d minus 1 zeros and of degree d minus 1 up to n, where the largest zero is up to n. So, but here I can also drop the n. I will make the conditions stronger. And let me write our condition. So what it means, so it means Lm of Rn f alpha. Using the linearity, I can write this as n times Lm of f alpha minus Lm of x of f alpha. But now I said that if it's realizable for an n, it will be also realizable for a much larger n. So think n arbitrarily large. We cannot really make a limit here. Yeah, then we see, I mean, we for sure need that Lm of f alpha is non-negative. Otherwise, if I make any n very large, this will become negative. And whatever, and this is also okay. So, so we need that. If Lm of f alpha is strictly positive, then if I make n large enough, it will kill the other part, because that's just a finite number. But if Lm of f alpha is equal to 0, then we need, and then no n help us, we need that Lm of x f alpha is equal to 0. Or in other words, no, that's what I wanted to say. Okay, so then we have to get this kind of forcing. You remember that's something which we saw already before. And putting that together, it gives me at least a hint what should be the general theorem. So theorem 4.3. Putative moments are realizable on and 0 if and only if the following condition hold. First of all, M underline of F is greater or equal to 0 for all F element PD. And sorry, this should be, let's intend it. So, and L M of F is greater or equal to 0 for all, and let's say for all F element PD minus 1, I have this. And if L M of F is equal to 0, then L M of X of F is equal to 0. And that's somehow the conditions. And these conditions are minimal. I cannot drop any of them. So this is, or what I've given you is not the proof. Where is the gap in what I have done? I put somehow this n to infinity. But if you think about what is happening in the proof, you will be able to construct it by a measure which will be supported on d plus 1 points. And one of these points will probably be at the right end corner at n, at the capital N. So if you make this n very large, so if you send it to infinity, this point will go to infinity, whatever that means. I mean, this is, I'm hand waving here, but if you have a kind, if you know something about compactification, you can somehow, you can give some meaning to the concept of having a point at infinity, but it's more than that. It's not the, this is not the Alexandrov compactification. So somehow this point may escape to infinity, and it can happen that you need to, for this construction, a point at infinity. And when this will happen, that is exactly the point here. When you get this extra forcing, you can get rid of that if you allow a point at infinity, whatever that means. Yeah. So, so if you just would plainly make the limit, you would not see this kind of thing. Okay. So. Now let me, I'm almost done and I should finish. So what does this mean in the case d equal to 2? So then P2, as we said before, is the collection of all polynomials which looks like that. L is an element of n0. And so we get the following. So we get Lm of x minus L times x minus L minus 1 is non-negative. And so this means that if we compute that out, this means M2 minus 2L plus 1, M1 plus L times L plus 1 is non-negative. And P1 is equal to the set of all x. This is just one polynomial x. So we get the condition that Lm of x is greater or equal to 0, which is just M1. And now the extra condition we have is if Lm of x is equal to 0, which is M1 is equal to 0, then I have that Lm of x times x is equal to 0, which is just M2. And that was exactly the extra condition which I discovered before. And so the good news is it's the only one. That's the only defect. The bad news is that in higher dimension, this will be actually more complicated. I mean, for higher degrees, this will be actually more complicated. That's I mean, that's how we actually came to it, because we were interested to do it for all degrees. And in higher degrees, you have to make a much more careful bookkeeping of this, because in each degree will introduce a new effect of this kind of property. And so I have then the only thing which I still have to talk about is conclusions, but this I maybe will do at the beginning of the exercises, the discussion of the exercises, which we will have in the next section, the next session. Thank you very much for your attention.
Thank you. Any questions?